Year 10, exact trigonometric values. So we're going to start with an equilateral triangle with sides of length 2 units. We're not going to worry about whether this is in centimetres, millimetres, metres, etc. We just know that the sides are of length 2. Can we work out the values of the interior angles in this triangle? It's equilateral, so we know that each of these angles is 60 degrees. Now, we're going to imagine that we split the triangle in half to create 2 identical right-angled triangles. So I'm going to split the triangle in half like this by drawing a vertical line down to the base from the highest point, and we create a right angle. And you're going to see a diagram of this in just a minute. So here we have the original equilateral triangle, and I've taken the right angle triangle that we created from the right hand side and drawn it out separately. Can we now work out the lengths of the sides and the value of the angles in this new right angle triangle? Yes, we can. We know that this angle here in the equilateral triangle is 60 degrees, and it's the same as this angle here in the right angle triangle, so that's 60 degrees. We know that the overall angle at the top here is 60 degrees, which means this angle here is half of that value, so this is 30 degrees. We already know that the hypotenuse of our right angle triangle is 2, it matches the 2 over here, and we know that the base of our right angle triangle is half the base of the equilateral triangle, so that is 1 unit. We can then work out the third side using Pythagoras' theorem. We would know that x squared plus 1 squared is equal to the hypotenuse squared, which is 2. X squared is equal to then 4 take away 1, which is equal to 3. So x is equal to root 3, and we will leave it in exact surd form. Now we have our fully labelled right angle triangle, we're going to focus on this angle here, the 60 degree angle, and we're going to ignore the 30 degree angle for the moment. So I am in fact going to cross it out so we can't see it or think about it for the moment. Let's label the hypotenuse, the opposite and the adjacent based on looking at this 60 degree angle. So the hypotenuse very clearly is the 2 over here. The opposite is very clearly the root 3, opposite our 60 degree angle, and the adjacent is the 1 over here on the base. We're now going to think about sine, cos and tan of 60 degrees separately. So we know from looking at our SOHCAHTOA triangles that sine of our angle, which is 60, is equal to the opposite divided by the hypotenuse. So sine of 60 must be equal to root 3 over 2. You can check that on your calculator and you will find that the sine of 60 has an exact surd form of root 3 over 2. Let's think about the cosine of the angle. We know that cos of the angle, cos of 60, is equal to the adjacent divided by the hypotenuse, so that is 1 over 2. So the cosine of 60 has an exact value of a half, or 0.5. Now let's try the tan of 60. We know that the tan of 60 is equal to the opposite divided by the adjacent, which is root 3 over 1, or simply just root 3. So interestingly, the sine, cos and tan of 60 degrees all have what we call exact trigonometric values. And you can check these on your calculator. Now this is really interesting because, for instance, if you work out the sine of most values, for instance, if you work out the sine of 58 degrees, that comes to a value of 0.848 0 dot dot dot, which is not an exact value. But the sine of 60 is an exact value. It's root 3 over 2. And there are certain other angles which also have exact trig values, and we're going to have a look at some other ones. So let's come back to the right angle triangle. And again, we're going to focus on one of the angles. This time we're going to focus on the 30-degree angle up here, and we're going to ignore this 60-degree angle for the moment so we don't get confused. And I'll scribble it out so we can't even look at it. Let's label the hypotenuse, the opposite and the adjacent, all based on the 30-degree angle's perspective. The hypotenuse hasn't changed, that's this, the 2, but the opposite is now the angle opposite the 30-degree angle, which is 1. This then leaves us with the adjacent to the 30 degrees, which is root 3. Same process as before, we're going to look at the sine, the cosine and the tangent of 30 degrees. Starting with the sine of 30 degrees, this is equal to the opposite divided by the hypotenuse, which if we look at the triangle is 1 over 2. So the sine of 30 is a half, or 0.5, which you may well recognise as a result you've seen before. The cosine of 30 is equal to the adjacent divided by the hypotenuse. So that is root 3 over 2. And the tan of 30 is the opposite divided by the adjacent. So that's equal to 1 over root 3. So the sine, the cosine and the tangent of 30 all have exact values. The tan of 30 is interesting because in its third form we can then rationalise the denominator, so multiply the numerator and the denominator by root 3, and we get an equivalent answer of root 3 over root 3. If you input tan of 30 into your calculator, it will give you an answer of root 3 over 3. So we now know the exact value for sine, cosine and tangent of 30 and 60 degrees. But there are some other angles that we are going to explore as well. We're going to have a look at a right-angled isosceles triangle with two sides of length 1 unit. Can we work out the values of the other interior angles in this triangle? And can we work out the length of the hypotenuse? The answer, of course, is yes, we can. These two angles here have both got to equal 45 degrees, so that the three angles in the triangle add up to 180 degrees. It's an isosceles triangle, so this side is equivalent in length to this side, which means that these two angles are also the same. So we have 45 degrees and 45 degrees. We can work out the length of the hypotenuse, which I will call x, using Pythagoras' theorem. 1 squared plus 1 squared is equal to the hypotenuse squared, which is x squared. So x squared is equal to 2, so x is equal to the square root of 2. So we know the hypotenuse can be labelled as root 2. So here's our triangle with all that information we've just calculated marked on it. We can choose either of the 45-degree angles to work with. It doesn't matter which. If you look at either of them, they both have the same opposite value and the same adjacent value of 1, and the hypotenuse doesn't change. But to avoid confusion, we want to focus on just one of them. So I'm going to cross out this one, and we'll focus on the one at the bottom. Let's label the hypotenuse, the opposite and the adjacent. So there's the hypotenuse, there is the opposite, and here is the adjacent. So, starting with the sine first of all, the sine of 45 degrees is equal to the opposite divided by the hypotenuse, which is 1 over root 2. Cos of 45 degrees is equal to the adjacent divided by the hypotenuse, which is 1 over root 2. The same value, so the sine of 45 and the cosine of 45 both have the same value, 1 over root 2. This leaves us with the tan of 45, which is equal to the opposite divided by the adjacent, which is 1 over 1, which of course just simplifies down to 1. So the tan of 45 has an exact value of 1. The sine of 45 and the cos of 45 can both be simplified if we rationalise the denominator. So we currently have 1 over root 2. We'll multiply the numerator and the denominator by root 2, which gives us a value of root 2 over 2. And again, if you input sine 45 or cos 45 into your calculator, you will find they both have the same value, and the calculator will give you a value of root 2 over 2. We can now summarise these exact trigonometric results in a neat table. So you'll see that we have all of the results so far placed in the table with some gaps. Now the gaps are there because we also need to know the exact trig values for 0 and 90 degrees. You can input these into your calculator to check that you get the same values. We'll be working on where these results for 0 and 90 degrees come from a little bit later on in a topic called trigonometric graphs. But for the moment, you can check on your calculator that the sine of 0 degrees is indeed 0. The cos of 0 degrees is 1. The tan of 0 degrees is also 0. The sine of 90 degrees is 1. The cos of 90 degrees is 0. And when you try and input tan of 90 on your calculator, you will get a mathematical error. And again, you will find out more about this a little bit later into your study of trigonometry. So we need to know what we can actually do with these exact values. So please don't use a calculator for this part. It's important that we can make use of these results without using a calculator. We're going to work out x in each of the following examples. So let's look at the first one. We have a right angle triangle and we've got to find this value x. Let's label the three sides of this triangle. Hypotenuse, opposite, and adjacent. Now, which two are we interested in? Well, we've been given the hypotenuse and we have to work out the opposite, which of course means we are looking at a sine question. So I'm going to write out my SO triangle. And of course, what I'm looking for is x, or the opposite. So the opposite is equal to sine of 30, which is s, multiplied by the hypotenuse, which is 10. But we now know from the exact result, and you can look back to the table to see this, the sine of 30 is equal to 0.5 or a half. 0.5 multiplied by 10 gives us an answer of 5 centimetres. And we have completed a trigonometric calculation using an exact trigonometric value with no need for the use of a calculator. Can we do this again? Look at example 2. We now have this 60-degree angle. Let's label the three sides of the right angle triangle. Here's the opposite first of all. Here's the hypotenuse, and here is the adjacent. Now, which two sides are we interested in working with? Well, we know what the adjacent is. We're trying to find out what the hypotenuse is. So let's make use of the cosine triangle, CA. So we need to find out what the hypotenuse is. So I'm going to cross out the hypotenuse. And the formula triangle tells me that I need to do the adjacent divided by cos of 60. Now the adjacent is 12, and we're dividing by the cos of 60. Rather than writing it out as a fraction, which can become very complicated, I'm going to actually physically write it out as a division, which is a top tip. That's 12 divided by the cos of 60, and we know that the cosine of 60 is equal to 1/2. So 12 divided by half, that's 12 over 1 multiplied by 2 over 1, which gives us an answer of 24 centimetres. And the last example, we have a 45-degree angle. Let's label up the three sides of the triangle: hypotenuse, opposite and adjacent. We're interested in the opposite and the hypotenuse, so this is a sine question. So let's draw out the or the sine formula triangle. Now we're trying to calculate the value of the hypotenuse, so I'll cross this one out, and we know that the hypotenuse is equal to the opposite divided by the sine value, so that is 8 divided by sine 45. We know that sine 45 is equal to root 2 over 2 from the work that we have carried out previously, so we now have to complete this calculation. Be careful here, there's quite a few steps of working. So that's 8 over 1 divided by root 2 over 2, which is 8 over 1 multiplied by 2 over root 2. Remember, if you are dividing by a fraction, we keep the first fraction the same. We change the sign from divide to multiply, and we flip or take the reciprocal of the second fraction. And that's how we conduct a fractional division. We can now multiply the two together. So 8 multiplied by 2, first of all, is 16. And 1 multiplied by root 2 is root 2. So the answer is 16 over root 2. But we can rationalise the denominator. I've run out of space, so I'm going to do the calculation up here. 16 over root 2, we need to multiply the numerator by root 2 and the denominator by root 2, which gives us 16 root 2 over 2, which simplifies down to a final answer of 8 root 2. So the final answer to this question is that x is equal to 8 root 2 centimetres in third form. You may need to go back through this third calculation as it's a little trickier than the first two. So let's look at 3 more examples. We need to simplify each of the following fully without using a calculator, making use of these exact trig values. So first of all, we have 10 sine 30. So that is 10 multiplied by sine of 30, which we know is equal to a half. Take away 6 multiplied by the cosine of 30, which we know is equal to root 3 over 2. Let's simplify as much as we can. 10 multiplied by a half is, of course, 5. A half of 10 is 5. Take away, and then here we can write 6 root 3 over 2, but this simplifies because, of course, 6 is divisible by 2, so the final answer is 5. Take away 3 root 3. And we cannot simplify that any further. Question 2. We have 12 tan 45, so that is 12 multiplied by tan of 45, which is equal to 1. Take away 8 multiplied by sine of 45, which is equal to root 2 over 2. This doesn't simplify significantly, but we can write it as 12, take away 8 root 2 over 2, and then, of course, 12 take away 4 root 2. Last example, 8 cos 60 divided by sine 45. So 8 cos 60 is 8 multiplied by 1/2, and we are dividing that by sine 45, which is root 2 over 2. So 8 multiplied by 1/2 is, of course, equal to 4. And this is being divided by root 2 over 2. Let's write the 4 as 4 over 1 so we can see the fraction clearly. So we'll keep the 4 over 1. We will change this to a multiplication, and we will flip the root 2 over 2 to 2 over root 2. Now, let's multiply the two numerators together. So we have 8 over root 2, but we will rationalise the denominator here, multiplying both the numerator and the denominator by root 2. So we have an answer of 8 root 2 over 2, which simplifies down to 4 root 2. Now, lastly, a very important point, you have to memorise these results. You could be asked to use them in your non-calculated GCSE paper. You might have to complete examples like the ones that we have already seen. So there are lots of different ways in which people like to memorise them. You might yourself want to go and do some research and have a look at some of the videos on YouTube about how to memorise them. This is one way that I have seen. I don't necessarily think it's the best way for everyone, but it is a method that I have seen some people use. So all of the existing results as they are set out are in the table. I'm going to write out some of these results in a slightly different way. So, for instance, sine of 0 is just 0, but that could also be written as root 0 over 2. Now, how does that work? Well, the square root of 0 is just equal to 0, and then if you divide 0 by 2, you still get an answer of 0. So it looks like just a slightly complex way of writing an equivalent number to 0, but bear with this, and you'll see why I've done it. Now, the sine of 30 is equal to a half. But we can also write this as the root of 1 over 2, because of course the square root of 1 is just 1. So again, it's a slightly more complex way of writing a half. Now, 45, the sine of 45 is already set up exactly as I want it to be, root 2 over 2. And the sine of 60 is already exactly where I want it to be, root 3 over 2. Now, the sine of 90 is interesting because I can write it as root 4 over 2. Some of you might have guessed this was coming because, of course, the square root of 4 is equal to 2. So really, I just have 2 divided by 2, which is equal to 1. Now look at the pattern that we have created. Sine of 0, root 0 over 2. Sine of 30, root 1 over 2, which is a half. Sine of 45, root 2 over 2. Sine of 60, root 3 over 2, and sine of 90, root 4 over 2. So this is one way I've seen people use to memorise these. They do, however, have to then remember to simplify these ones and write them out in their simpler format, rather than leaving them like this. Can we do something similar with the cosine? Let's have a look. So the cosine of 0 is equal to 1, and like here, I'm going to write that as root 4 over 2. The cosine of 30 is already exactly where I want it to be, as is the cosine of 45 degrees. The cosine of 60 I'll rewrite as root 1 over 2, and the cosine of 0 I'll rewrite as root 0 over 2, using the same justifications we did for sine. So, root 4 over 2, root 3 over 2, root 2 over 2, root 1 over 2, and root 0 over 2. It follows the same pattern as sine, but backwards, so in reverse order. And then we have the results for tan. You can see those listed in the bottom of the table as well. So using some method, either by memorising the results or using a trick like this, or learning where the results came from by memorising the techniques we saw with the right-angled triangles from the start of the video, you do need to memorise the sine, cos and tan of these 5 angles, 0, 30, 45, 60 and 90.